Hello everyone, my name is Anton Romanov, and in this video I will tell you about my job. I work as a software developer. I work for a company called Syntacor. Here you can see on the screen its main page on the internet. It designs processors and develops software for them. Briefly, I'm making Android OS operating system faster and more economical for certain processors, and more specifically for processors with RISC-V architecture. What is architecture, and more specifically the instruction set architecture? It is the interface between the computer's software and hardware, and also can be viewed as the programmer's view of the machine. Computers do not understand high-level programming languages such as Java, C++, or most programming languages used. A processor only understands instructions encoded in some numerical fashion, usually as binary numbers. Software tools such as compilers translate those high-level languages into instructions that the processor can understand. Software is divided into two layers: applications and the operating system. The application can be a browser, a file manager, a messenger, and so on. The operating system manages the computer, provides applications with access to devices, and regulates the operation of applications. In turn, the hardware is also divided into two layers: microarchitecture and the digital level. Microarchitecture is the way a given instruction set architecture is implemented in a particular processor. The digital level defines which primitive circuits are used in a microarchitecture. In this slide, I present the compatibility of the operating systems and the instruction sets. Processors implementing the same architecture are listed at the bottom of each column. So which operating systems we have here? Apple macOS, Windows, and Android /Linux. Android contains Linux kernel as its part. And Apple's macOS supports now only ARM architecture. At least the latest devices of Apple have ARM processors. Windows operating system supports both architectures, ARM and x86. And Android Linux supports all these three architectures: ARM, x86, and RISC-V. Mass market. In this table, I have given examples of devices that are mass sold on the market. All the phones have processors with ARM architecture. There are no devices with RISC-V processors. History of programming languages development. How does one write a program? In order to write a program, a person needs to learn a certain language. Such a language is called a programming language. Following the rules of a particular language, a person writes a program that he needs. At first, there were only machine languages such as IBM 701. Then gradually assemblers and assembly languages such as ARM began to appear. Since 1972, there have already been languages that are convenient for humans to write programs. All languages presented here except IBM 701 are used and needed today. Fibonacci sequence. Fibonacci sequence is a sequence in which each element is the sum of the two elements that preceded. In the bottom row of the table you see the Fibonacci indexes, and at the top you can see Fibonacci numbers. Program written in human language, C language. Line numbers on the left are not part of the program. You can see a program written in a human language. In this case, it is language called C. Each program consists of procedures. The slide shows a procedure named fib. The first line contains the type of the procedure's return value, the procedure name, the type, and the name of the input parameter. On lines 3 and 4, local variables are declared and immediately initialized with values 0 and 1. There is a for loop on line 6. First, it declares and initializes the variable I to the value 2. It checks the condition less than or equal to n, and, if true, enters the loop's body. After executing the body of the loop, the ++i action is performed. Lines 8 through 10 contain the body of the loop. On line 13, there is a return from the procedure with the transfer to the value from variable b. Architecture von Neumann. A computer has a central processor and a memory. These devices are connected by bus. The processor contains registers and arithmetic logic unit. We're most interested in registers, which are called user-accessible registers. Such registers can be read or written by machine instructions. Assembly language. A computer, or more specifically a processor, does not understand a human language such as C. A program written in C must be first translated into assembly language. Assembly language is a form of machine language that is easy for humans to understand, and I will explain this form for you. Let's start with a simple assembly instruction on line 19. It reads a number from the W8 register, from the W9 register, adds these two numbers and writes the resulting sum to the W8 register. On line 3 is the str instruction, which means store. It takes a number from the processor register and writes it to memory. In this case, it reads a number from register W0, which contains the parameter n. It adds the number from the SP register to 28 and uses the sum as an address in memory. It will write the parameter to this address. The LDR instruction does the same thing, but in reverse. It reads from memory and writes to the processor. On line 3C, you see instruction B, which means branch. This is an unconditional jump. It transfers program execution to the LBB01 label, which points to the instruction on line 11. That is, execution will transfer to the LDR instruction on line 11. The subs instruction on line 13 subtracts values from registers W8 and W9 and sets the flag to a special processor register. The flag can be greater than, equal to, or less than. The following instruction b.gt means branch if greater than, switches to the label if the flag greater than is set in that register. Numeral systems. A numeral system is a writing system for expressing numbers, that is, a mathematical notation for representing numbers of a given set, using digits or other symbols in a consistent manner. The same sequence of symbols may represent different numbers in different numeral systems. For example, 1 represents the number 11 in the decimal numeral system, the number 3 in the binary numeral system. In this table, I have presented the correspondence of numbers from 0 to 12 in decimal and binary numeral systems. Machine language. The processor does not understand Latin characters, decimal digits, and so on. Therefore, in order to execute a program, the assembly instructions must be translated into machine form. On this slide, you can see the assembly instruction on the left and its machine representation on the right. 1110 is a condition, or rather its absence. I will explain what it is in one of the following slides. 00 is an opcode, that is a code for data processing instructions. Addition is an arithmetic operation and it is a data processing instruction. 0i means there is no immediate operand. Here only registers are in use. 0100cmd is a command. Addition has such a code. 0s means this instruction does not set a condition flag. For instance, instruction sub s does set such a flag. 0110rn is 6 and it is a number of the first source register. Here we can see R6 is the first source register of this instruction. 0101RZ is 5 and it is a number of the destination register which stores the resulting sum. Here R5. The destination register which will store the resulting sum. I will skip shamt5 and sh now. 0111rm is 7 and it is a number of the second source operand. Here it is, second source operand, which is register R7. The sub instruction has a different command number 0010. Everything else except the operands is the same. LDR 01 opcode is the opcode of memory handling instructions. IPUBWL 1U means that the processor should add the value from the register with the immediate operand, which is 26 in this case. 26 here, immediate operand. 1L tells that this is a load instruction. Load register. If it is 0, then the instruction is store. 0101 RN is R5, which is the source operand. 1011 RD is a destination register, R11. Processor writes a value from the memory to the destination register. And 11010 is 26. And it is the immediate operand. BLT, branch if less than. 1011 condition is different from the previous ones. It means less than. 10 up, it is code of jump instructions. 10 funct is the conditional jump code. There are also unconditional jumps and procedure calls. Both have their own code, which is called funct. 11, I pulled it out of thin air. It is a target instruction number and it matches to their label. Here it is, their label. And I just pulled it out of thin air. Instruction handling cycle. Machine instruction is executed in the processor in 3 stages: fetch, decode, and execute. Fetch. At the fetch stage, a processor receives an instruction from memory. Decoding. At this stage, the processor finds the opcode in bits 26 to 27 here, and from which it draws a conclusion about the structure of the entire remaining instruction. Execution. At this stage, numbers are extracted from the registers and they are sent to an arithmetic logic unit to calculate arithmetic operations. If instruction has an immediate operand, then it goes immediately to the arithmetic logic unit. Also, this unit requires an operation type: addition, subtraction, and so on. Microarchitecture example. This is an example of a real microarchitecture. Intel has shared a diagram of its microarchitecture. It consists of a front end, an execution unit, and a memory interface device. The execution engine, in turn, has an arithmetic logic unit for calculating operations. Android. Simply put, Android consists of applications, a runtime environment, and a Linux kernel. Implementations of human languages. A processor does not understand human languages. Therefore, some processing is needed to execute a human-written program. This processing can be a translation of the program into a machine language. A program that translates any program written in assembly language is called an assembler. Assembler is an implementation of an assembly language. C programming language has a similar implementation, which is called a compiler. But the Java language has a different implementation. It consists of a compiler and an interpreter. The compiler translates the program from the human language Java into an intermediate language. Then the interpreter starts on a computer. An interpreter is a program written in C and translated into machine code so that it can be run on a processor. The intermediate code is called a bytecode. The bytecode is passed to the running interpreter. The interpreter executes the bytecode. Comparison of two implementations. The interpreter executes the bytecode. The bytecode is much smaller than the machine code, but the interpretation itself is very slow. The compiler, on the other hand, produces fast machine code, which unfortunately is large. 90% of the time a program runs, only 10% of its code is executed. You can easily find out the size of the same apps for both Android and iOS platforms. Instagram weighs 375 megabytes for iOS and only 75 megabytes for Android. The difference is 5-fold. Hybrid implementation. But fortunately, there is a hybrid implementation. Any program consists of procedures. The procedure that is called first is called main. Rarely called procedures are called cold. Frequently called procedures are called hot. Hot procedures make up only about 5% of all procedures. The interpreter can count the number of calls to each procedure. Usually, a procedure is considered hot if it has been called more than 15,000 times. The interpreter can send hot procedures for further compilation into machine code. After the compilation is complete, the interpreter will run the resulting machine code. An implementation that contains both an interpreter and a compiler, let's call a virtual machine. Code path. Let's follow the path of an Android application written by a human. First, it is translated from the source language Java or Kotlin into an intermediate code, Java bytecode. Then it is translated into Android bytecode called DEX. After that, DEX bytecode can be loaded onto a device such as a phone. When the user clicks on the application icon, the Android Runtime virtual machine is launched. It interprets called procedures and compiles hot procedures into the target machine code. If we are talking about today's phones on the market, this is ARM code, although a developer can experiment with x86 and RISC-V. What I'm doing is improving the support for RISC-V on the Android system. My patches to AOSP, Android Open Source Project. This is my page in the Android Open Source Project web interface. You can familiarize yourself with this by following the URL at the top. It's valid. Optimizations I will explain. I will explain only 3 of my optimizations. They are implemented in 4 patches on this page. There are such logical operations as AND, OR, XOR, and NOT. You can see the corresponding truth tables on this slide. They can also be applied to sequences of bits. I also showed a circular shift of the sequence 00010111 by 1 bit to the left. This shift is called a rotation. In this table, I compare 3 architectures by 3 types of instructions. The ARM architecture has all 3 bitwise instructions with the negated right operand. In the intermediate representation of the compiler, there may be pairs of NOT and AND instructions, such as from the bottom left. Such a pair can be converted into a single AND NOT machine instruction. Before my patch, there was an optimization in the compiler that performed such a transformation for ARM. My patch extended the application of this optimization to RISC-V. There is no rotate left instruction. It is briefly referred to as roll in ARM architecture. The Java language has a built-in rotate left procedure that performs such a shift. Before my patch, calling this procedure turned into a pair of ROR and NEC machine instructions for all 3 architectures. My patch converted this call into a single roll machine instruction for RISC-V and x86 architectures. it may be necessary to shift one value and add another value to the result. This is so common that architectures have instruction that does it all. It may be necessary to shift one value and add another value to the result. This feature is widely available in ARM. In ARM, it can be a subtraction. The shift distance in ARM takes on a variety of values. In RISC-V, the distance can only be 1, 2, or 3. Such an operation can be, for example, accessing an array element. Why convert a pair of instructions into one instruction? Firstly, it is obvious that one instruction takes up less space. Secondly, one instruction is executed faster. Why? At least because of the need to decode only one instruction and not two. Fewer registers are used, fewer memory accesses, and memory accesses are very slow. So this is the end of my video. Thanks for watching. Subscribe and write comments. And of course, share my video. Goodbye.